And then question 4 over here, 4.1, they're saying prove that in any arithmetic series, Sn equals n over 2 in brackets multiplying a plus l, close brackets. This is a 4-mark question for the proof of this guy. So we're going to rewrite this over here. So this is a slightly different form. We have an l over here and we don't have an l from our initial formula, but we do have an n over 2, so that part's common. So to break it up to see what actually represents the last term, it's quite useful to split up our a, because a plus a n minus 1 times d. So I split up the a, we have an a separately over here, and then our a n minus 1 plus d, which looks quite familiar because that is just what our sequence is for an arithmetic sequence, which means if we split it up like this, we have our first term over there, which is our a, and this represents our last term. It can represent any term in our sequence, but in this case, it's representing our last term. So this is just a different way of saying a plus l. If we rearrange the letters, splitting up our a over here, which gives us our first term, and this portion gives us our last term. That is just additional information. Sometimes they could give us this formula to work with to then solve the proof. But in this case, they've just given us l, so we need to set things up. So what we need to do is we need to basically break up everything that this represents. By that, I mean Sn is a plus d plus a plus 2d plus plus l. Because what a series represents is the first term, which is a, plus the second term, which is a plus d, because the difference is being added to the first number, and then adding d again and repeating until we get to l in this case, because we're working with our last term here, not this a bracket n minus 1 times d as the last term, which means it's from the first term, adding the difference and repeating. We don't have to know how many terms there are, and then we do know that there is a last term, and that is represented by l. So this is working left to right. But then what we need to do is also work from the l's perspective, and that means we have our Sn equals l plus l minus d, because l minus d would take us back one term, plus l minus 2d plus plus a. Okay, so this is the setup of the proof over here, where we have it going forwards and then we have it going backwards. And now that we have this set up, what we need to do is do elimination, but we need to add them based on how we would approach things in simultaneous equations, because we want to add them up. Because right now we have a whole bunch of things, but we're trying to cancel them, okay? And we don't have this 2 here. So what we're doing is we're adding Sn plus Sn gives us 2Sn. This is good for us because we have a 2 over here and we have an Sn that we need in our final proof. And then at this stage, what we're doing is we're going first term plus first term. So we have a plus l. And then as we can see over here, we have a plus d plus l minus d. But this positive d and this negative d cancel each other. And then we're left again with a plus l. And we can do this again over here where we will be left with plus a plus l, and all the way to the end where we will once again have a bracket of a plus l. Okay, which means this just goes on forever. All the differences cancel each other. And if we just have a plus l going on forever, what that means is that we have n amounts of a plus l, because it doesn't matter how many a plus l's we have. We just know that we have n amounts, and n represents however long we decide to add up for, which means we can remove some of these additionals by just substituting n in over here, saying n times a plus l. And that's very close to this final answer over here, but we're just missing our 2 on this side, and the 2 on this side comes from this side, because if we divide by 2 over there, we divide by 2 over there, and we're left with Sn equals n over 2 multiplied by a plus l. And that is our final answer for 4 marks, proving this arithmetic series. And then 4.2 over here says calculate the value of the sigma, starting with 1 as our first input for p, going all the way up to infinity, and here is our geometric sequence. So it is a 4-mark question, and we just need to work with the correct formula, considering it's going all the way up to infinity. So if a geometric sequence is going all the way up to infinity, it means that this is what we're working with. So I'm going to go ahead and rewrite this for us. So we have S infinity equals a over 1 minus r, when our ratio is between -1 and 1. Okay, we only work with our inequality when they're talking about convergent. This is just the restriction, and that means our ratio is going to be some sort of fraction. It won't be -3 or +3 or anything outside of this range, not when we're working with a sum to infinity, which means we need the value of a and the value of r to solve for the sum of infinity. And that means we have to get our first 3 terms. So if we go ahead and plug our first input into here, we have 2 multiplied by 3, close brackets, to the power of of 1 minus 1. And 3 to the power of 0 is just 1, so 2 multiplied by 1 is just 2 over there. And then term 2 is plugging in the second input over here, which means our second input is 2. So we have 2 multiplied by 3 to the power of 1 minus 2. And this equals 2 over 3. We then do the same thing for term 3, where we rewrite this formula. We just make it to the power of 1 minus 3 over there. And that equals 2 over 9. So now we have the values of T3, T2, and T1. And this is great for us because T1 is our A value. So if we want to plug that in so long, we can go ahead. So our A is 2 over there, and then 1 minus our ratio. Our ratio, as we did in the previous question, is T3 over T2 equals T2 over T1. We can just work on either side, okay? Which means 2 over 3, which is T2, over 2, which is T1, equals 1 over 3. And this fits the restriction over here that our ratio needs to be between -1 and 1. And a reminder that our ratio is this number multiplied by the ratio gives us the second term and repeats. So we can just go ahead and plug 1 over 3 into r's position, and then we can go ahead and solve for s infinity, because s infinity equals 3. And this is the final answer for every single number in this sequence added up to infinity as it approaches closer and closer to the limit of 0. And that just earned us 4 marks. And then 4.3 says, in a geometric series, the sum of n terms is given by Sn equals p brackets 1 minus brackets half brackets to the power of n close square brackets. And the sum to infinity is 10. So we have two different things that we're working with for a algebraic type question. So 4.3.1 says, calculate the value of p. So p over here is unknown. So if we rewrite the information we've been given, we have s infinity equals a over 1 minus r is the formula we're working with, and they told us the sum to infinity equals 10. So this guy equals that guy, which means we don't have an a, and we need to see if we have an r. And then they've also given us Sn equals p 1 minus a half to the power of n close brackets. And it's always important in these questions to rewrite the formulas we're working with. So here we rewrote this formula. Here they gave us a variation of this formula, but let's also rewrite this formula, because here we rewrote the normal formula that we're working with. So this is the one part, and this is the other part that we're working with. And what is useful to see is that this r to the n, that anything to the power of n is our r. This is just in a different rearrangement, meaning that they swapped the 1 and the r and the 1 and the r to the n, okay? Because they took a negative out here, which means they went 1 minus r to the n. They took a negative out there, which means they went 1 minus r, swapping them. And the negative, they just cancel each other out, which means we're not far away from this form over here, because what we can gauge is that this 1 minus r in our denominator is gone. A doesn't necessarily mean p because this is missing, okay? But as we can see, now that we rearrange this bracket, we have 1 minus r to the power of n, and we have 1 minus r to the power of n, which means in this formula over here, our r is a half. So we can then go ahead and solve for a, because s infinity equals 10, so 10 equals a over 1 minus a half, because we saw that r represented a half because they were both to the power of n, and that is representing our ratio in both formulas. From there, we can simplify this because we have a 1 minus a half is a half, and this equals 10, and then 10 multiplied by a half is 5. So 5 equals a. So we've just solved for the value of a. So at this stage, we don't have enough information to plug in here to get p, but we do have an a here, we do have an r over here, which means we can plug our a and our r in, and then we can see how the numerator and the denominator simplify to make p, because Sn is still unknown. We're not trying to solve that. A we just solved for as 5. 1 minus 1 over 2 to the power of n over 1 minus r is 1 minus 0.5. This is also our 1 over 2 over there, which means we have 5 over a half. If we simplify 1 minus 0.5, that's a half. And then we have 1 minus 1 over 2 to the power of n, because then at this stage, 5 over 0.5 is 10, and the brackets are unaffected because these were just numbers that we could simplify, which means if we reference our initial form, we can then see that the 10 equals p over here because the form is exactly the same. This is where we came from. We then rearranged our formula by subbing in our a and our r, and by simplifying the numbers, the location of p is represented by 10 in this new condensed formula, which means we have just calculated the value of p for 4 marks because p equals 10. So then 4.3.2 over here says calculate the value of the second term. So this is also 4 marks, but it could just be a 2-mark question in another paper, depending on what we did first, because there's another way to solve for p by treating anything to the power of n as 0, because as we approach infinite numbers, it almost becomes 0. It gets smaller and smaller and smaller until it becomes negligible and basically becomes 0. So we could have approached 4.3.1 this way by just making this r over here 0 and then doing everything else we did for 4.3.1 over here, but we worked out our a and our r already, so that means we can just rewrite them in our equation over here because they just want the value of the second term. And if we have a and we have r, we can get our value of our second term by plugging it into our sequence formula, because we calculated our value of a as 5 over there, our value of r we saw was 1 over 2, and then they want the value of the second term, which means n is the second term, so we plug in 2 over there minus 1, and this gives us 2.5 as the value for T2. Okay, and in another test that would give us 2 marks. In this test it gave us 4 marks depending on what we worked out whether we solved for a and r only in 4.3.2 and we tried the other method in 4.3.1.